My name is Mark Lythgoe. I'm Director of the Centre for Advanced Biomedical Imaging at UCL, which is the experimental imaging facility. And what we try to do is to develop the new imaging techniques of the future, the new brain scanners, the new heart scanners, things that are genuinely going to transform the way we look at the mind or the body. So how has imaging changed our view of the body? I mean, maybe it's obvious in some respects. We have MRI scanners and brain scans and X-rays and CT and ultrasound and fetuses. But for me, it has changed how I understand fundamental biological processes. For example, if we start out, all of us, as a single cell, and I cannot imagine how we grow from a single cell up to this multi-billion cell organism. And then the other day, I was shown a video from a technique called light sheet microscopy that we have here in Cabby. And it allows us to image every single cell as it grows, divides and changed. So on this video, they follow a fruit fly larvae as every single cell grows, divides and changes, and you can see the cells grow, and then they sort of jostle each other. Then there's 4, there's 8, there's 16, there's 20,000, there's millions of these cells, and suddenly the whole structure starts to evolve of this animal. There's the spine and the head and the segments, but I'm watching this in real time, and that is what is happening just a million times over in our own body as our brain grows and develops. All the gyri, the blood vessels, all come together, each individual network, and I'd not got it. I had not got that concept, and then I saw that video and it completely changed the way that I'd look at my own development. And I think it's only imaging that gives us those shortcuts for concepts. Mathematics can give you a shortcut, but that's quite limited. You have to understand the mathematics, the language of mathematics. But an image can quite simply get over a concept in a way, well, certainly that I haven't been able to find through other methods. So why do we use light? We can use certain types of light, bioluminescence. These are your fireflies that you see, which are very rare these days, at the end of summer, and they light up, and it's very bright light, the brightest form of biological light. And what you have to do is to take the gene that creates that light, and you can put it into the body, you can put it into cancers. And literally, just with a chemical reaction, the light will come out of the tissue and give us an indication of how that tumour is growing over time. And it's relatively easy, as I said, to get the light into the tissue. It's a big laser, a fibre optic, it fires the light in. The problem is getting the light out. But the light will be absorbed by certain pigments, chromophores, and in red blood cells, oxyhemoglobin, deoxyhemoglobin, absorb this light, then they thermally expand. And as they thermally expand, they give out tiny ultrasound waves. And we get these beautiful three-dimensional pictures of the blood vessels around tumours by creating light into ultrasound inside the body. So this is the Invisible Man project, where we make tissues completely transparent. If I was to put the heart or the brain in your hand, it is literally, you can't see it. Not that you can see very, very faintly some little streaks of tissue in there, but it's virtually completely, you can see it just coming through there tight, but the tissue is virtually completely transparent. And once you've made tissue transparent, then you can get light out of it. You can investigate these small genetic or molecular effects. What we do is to make the tissue completely transparent to get the light out. So this is part of the liver, and we're looking to see if we can detect liver metastases. Now the blue bits are the normal liver, and anything that's gold is the tumour, the metastases within the tumour, and they're lighting up differently to normal tissue, so we can see what's normal and what's cancerous. And the first time that we did this, we were just blown away by the fact that there is so many tiny micrometastases that we would not be able to pick up, let's say, on our MRI scan or the nuclear medicine scanner. This gives us detail virtually down to cellular resolution, and allows us to look at the genes that are switching on or off these tumorous processes. And it's only possible because we can make the tissue transparent and then get the light out of the tissue. This is definitely a stepping stone to develop a series of technologies. The first thing is that we have to be able to get light out of tissues, and we've been able to do that, and we've been able to see within the brain the level of connections that we have between different cell types in a way that we haven't done before. And of course, once you understand the fundamental wiring diagrams, then you can start to understand how a drug, it's Parkinson's, Alzheimer's, would interact with those networks. And in terms of the heart work, what we want to be able to do is to be able to see how individual genes would contribute, let's say, to the predisposition for heart attack. In the same way, you'd be looking for the contribution of genes to cancers. In order to do that, we need to be able to get a three-dimensional map of those genes when they're switching on and when they're switching off. Which are the genes that switch on or switch off, and then move that heart towards a heart attack or move it towards cancerous tissues. And it's by creating this invisible tissue that allows us to get the light out from these genes and see those processes that we just haven't been able to before.